Hello, hello, mushi mushi. Good evening, good morning, good afternoon, good night to everyone who's watching. We will begin in 2 minutes. This is also an audio test, so hang on a minute. We are gonna start soon. Okay, it's 8 p.m. and I think everybody looks ready. Let's begin now. All right, so hang on a minute. Let me get my internet shenanigans settled and bam, there we go. So we are live. We are live for today. This will be the last session for our live solving. So once again, welcome everybody. Hello, I am Zong Yang. I'm your tutor for today and we'll be doing paper 6 set 2 for summer 2025. So we'll be doing physics IGCSE subject code 0625. So if you're not taking this subject, please help yourself. But for those of you guys who are here for our IGCSE Physics paper 6 set 2, welcome. For those of you who are here for the wrong paper but still you like to hear some tips and tricks, welcome as well. And so for today's session, we'll be going through the entire paper as per usual, and we'll be solving each question in detail. So for everybody here, right, in the live section, please, you can take a look at the chat over there. At the chat section, Narayan Sir, our friendly tutor, will be answering up to 10 appropriate questions from the chat, okay? And basically, these chat questions, right, will be any IGCSE physics questions or anything that got to do with whatever I'm solving. And this will come as a first come, first serve basis. And Narayan sir will be looking through all these questions. So do say hi to him when you are in the chat, all right? So without further ado, let's begin today's session. All right. Okay, give me a moment. Techie stuff is always a little bit iffy sometimes. Oops. There we go. Okay, then standard. Okay, there we go. You should be able to see my paper now. Yeah, final session. All right. I'm not a great artist, but hopefully this works. All right. Hello, are you working? Here it goes. Here goes nothing. All right. So yeah, that looks good now. Let's begin today's paper. All right. So remember, this is paper 6 set 2 and this is summer 2025, okay? Please, for everybody who is doing this paper, who is joining me to do this paper together, please remember to to print this paper in a 1:1 scale. All right, this is very important because there's a lot of diagrams you need to draw, especially those that need to be scaled. And some skills like diagram construction, drawing things to scale, this can only be cultivated when you actually print the worksheet and then work together with me. So that's one thing. And next, right, is when you're doing this kind of worksheets, please make sure to bring a ruler. You can see this, right? This is a ruler, yeah. So please bring a ruler, please bring a protractor, please bring your drawing tools. And when you are drawing these diagrams, please, instead of using a pen, use a pencil, okay? A pencil allows you to erase it when you make a mistake. It's a lot neater, and our poor invigilators in Cambridge don't have to squint at your handwriting, all right? As for what you need to write down over here, write in pen, of course, but for everything else, like drawings and diagrams, pencil will be the way to go. All right, let's begin. Okay, so question number one. Question number one is, a student determines the internal diameter D of a test tube, and the apparatus is shown here in figure 1.1. All right, so right here, figure 1.1, the test tube is over here. We are to determine the internal diameter of this thing. All right, it's right here. Okay, And so what do we do? What the student do is, the student fills a measuring cylinder with water up to the 100 centimeter cube mark and pours some water from the measuring cylinder into the test tube. And a full-size diagram of the bottom part of the test tube is shown here. Here we go, right? This is the full-size image. But the thing is, you don't know what is full size unless you print this out on one-to-one scale, all right? So please, for all students who wants to take this seriously, please print this nicely on a piece of paper, or you can get one of those 10-year series and this is printed nicely as well, okay? So on figure 1.2, measure the height h in centimeters to the nearest millimeter and record your result on the top row of table 1.1 in page 4. So let's move down. So I have already done the measurements by scaling my paper to the screen one-to-one with a piece of A4 paper, okay? And let's take a look here, all right? So we are supposed to record the results at page 4. Page 4 is over here, okay? If you see this over here, all right? So if you use a ruler and you measure this nicely, right, you should be able to get h to be 3.4 centimeters, okay? All right, so for this, of course, use a ruler. This is pretty common sense to most of you guys by this time already, yeah? So this is the height h over here should be 3.4 centimeters, okay? If you use a ruler to measure this properly, okay? And of course, you write this down in page 4. By doing so, you should get your first mark, okay? Now, let's move on to part 2 for this question, okay? Part 2, you see, right, it shows the volume of water that's remaining in this measuring cylinder. So remember, right, this, at first there's 100 milliliters of water in the measuring cylinder, and we poured away a certain amount for this, okay? So what is this reading? This reading R, if you take a look here, right, R is equals to 90, right? And then each of these small little marking is 1 cm cube. So 90 minus 1 is 89 centimeter cube, right? So we take the reading R and record the result on the top row of table 1.1. So just now we had 89, right? So 89 centimeter cube here. Okay? Yeah. All right. Just like that, 2 marks already. Yeah? Simple, right? Then next, we are to calculate the volume V of the water poured into the test tube and use this equation. V is equals to 100 centimeter cube minus R. Do you remember just now, I did say, right, we have about 100 cm cube of water in the measuring cylinder and we poured a certain amount, which is that, right, V into the test tube. So we already have the remainder R, which will be 89. So V is equals to 100 minus 89. And that should get you 11 centimeter cube, okay? Just like that, the third mark is done over here, like this, okay? Very simple, right? 3 marks for 3 very simple measurements, okay? Now that's done. Okay, there we have our completed table. 3 numbers over here, okay? Yep, so next, the student in part B, right, adds more water from the measuring cylinder into the test tube, and then they measure the new height h of the water in the test tube and measures the new reading R of the water remaining in the measuring cylinder, and then calculates the volume of water V in the test tube and repeats this procedure for 3 more values of H, R, and V. So if you remember how to do, as a good habit, right? You should do at least 4 or 5 repeats of the same experiment with the different variable, right? With one of the variables that the variables over here, right? You're supposed to change it to make more you're supposed to repeat the experiment a few more times with different values of R to have some sort of table reading, and all these numbers are already given over here. All right. So the student's result is calculated as here in table 1.1. So it's also important to avoid the line of sight errors, or should I say parallax error, while reading the scale of the measuring cylinder. So we are to describe how such an error are to be avoided, and we may use a diagram, okay? So pretty much this is a very straightforward thing, right? You're supposed to avoid line of sight errors. So what does that do? So for example, if you have this measuring cylinder over here, right? Then you have all the graduations, the markings over here, right? If the water level is here, okay, like right here, okay. Oops, this is really bad drawing. Give me a second. So if the water level is like somewhere around here, okay, right? And we have to remember the meniscus, okay? You have to put your eye something like this, right? Directly over the reading. So vertically over the graduation reading. So once that is done, we can just write down the answer as the student, right, should take measurements, okay, vertically, right, above the graduation markings. Okay, just like that, your full 1 mark is done. So basically, how do you get your 1 mark? Essentially, anything to do with, right, the scale, read the scale like what, right angle above, or at eye level, or perpendicularly. Anything of that sort will get you your 1 mark, okay? My answer is just one of many. Oh, all right. So far so good, yeah? Let's move on. Okay. My favorite part, graph plotting. This is gonna be a massive pain, yeah? All right, so let's begin this one, okay? So we are to plot a graph of V in cm cube in the y-axis against h, cm, right? On the x-axis, okay? And we are to start the axis at origin 0, 0. Please remember to read this, yeah? Start the origins at 0, 0. Everything be given to you. All right, so draw the best fit line. So once again, please take your trusty ruler. Let's begin. First, let's draw the axis, okay? The axis should always be drawn first. One over here, okay? Please ignore the very badly drawn axis over here. Oi, 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 this is bad. Wait, okay. Then you should come here. Okay, I need to be very careful. Okay, there we go. Axis number 2. There we go. Okay, so as you said over here, right, the graph is the y-axis is volume V, right, in centimeter cube. Okay, please remember to write this over here. And on the x-axis over here, h, right, over here is supposed to be h is over here in cm. Okay, let me just reduce the size a little bit so you guys can see the full graph. Yeah, right, like that. Okay, so next thing we need to do is we need to start drawing the graduations, the markings on the side of each axis. So let's take a look, right? So for h over here, we start at 3.4 and it goes all the way to 13. So the sensible way to do this is, let's see how many graduations we have over here. So how many boxes we have? We have one big, 1, 2, 3, 4, 5, 6, 7, 8. So 8 times, maybe we can use 16 as the maximum. Then we can work our way back down. 16, 14, 12, 10, oops, 8. This should be 6, this should be 4, and this should be 2. Okay, yeah, please draw this cleanly and as neatly as you can. Okay, so x-axis is done. Let's take a look at the y-axis. The y-axis wants you to use V. V starts at 11 over here and ends at 47. So we can maybe have a range of about 0 to 50, all right? So let's take a look here. How many boxes we have over this side? So maybe let's see, 1, 2, 3, 4, 5, and 6. 6 big ones. So maybe we can have each big box to be 10, or in increments of 10. So 10, 20, 30, 40, 50, and 60 like that. So now we have our scales done. So if you take a look at how this should look as a so-called model answer, right? Let me show you. This should be our first step. It should look something like this. It's really nice and neat, yeah, okay? So this, please take note, draw these nicely using a pencil and use a ruler, okay? Don't freehand this, yeah? All right? Okay, so that's done already. Let's start plotting the points into our graph. So let's take a look over here. All right, so first point, we just ignore R over here. We just want V and H, right? So H is 3.4, V is 11. So we go, let's take a look over here. Where is 3.4 on the x-axis? So this is 3, right? 3, and each of these is 0.2, so 3, 3.2, 3.4. Okay, so 3.4 and 11. Each of these small boxes, right, is 1. So 10 is up here, 11 should be here. So 3.2, 11 should be somewhere over here, okay? Something like that, okay? Please remember to draw your crosses, right? Or your little plot points, right? Use a sharp pencil and make sure it's a very dark pencil, like a 2B pencil, so you can see where exactly you are plotting, okay? Mine, I don't really have a choice. I only have this, so, okay? So let's plot down the rest of the numbers. Okay, so 3.4 and 11, that's the first one. Second one is 5.0. 5.0 is right here. And 84 and 16. So next is 16. 16 is here. So you draw a line up here to here. This is 16. This is our second point. Okay, so that's done. Third point is let's see, 7.6 and 25. So 25 is here, right here, right in the center between 20 and 30. And 7.6 should be here. So this is 7, 7.2, 7.4, 7.6. Here we go. So let's draw a line all the way up here, and it should meet here. Okay, just make sure the center of your cross should be exactly where the point should be. So let me just do this nicely, okay? Right there. That's our third plot. Our fourth plot will be 10.3 and 36. So 10.3, this is 10, 11, 10.2, 10.3 is the center between these two lines over here. And then 36, which should be our value over here. This is 35, okay? 36 is right here on top. So our number should be, our next plot should be here. And finally, 13.6, 14, 13.8, 13.6, right here. And let's see, 47, 47, 45, 46, 47, right here. So it should be somewhere over here, okay? And here, this should be the point. Oh, that's bad. Wait a second. There we go. So our five plots are done. So if you take a look at the model answer, which I've done already beforehand, it should look something like this, yeah? So do take note, your plots should be nice and small, and also should be drawn with a sharp pencil, okay? The sharper your lines, the sharper your plot points, the more accurate you can get, okay? Now, next, we need to draw a line of best fit, okay? So, and the line of best fit, right, that if you do know, right, 0 is also somewhere you must start from, because this is well, the thing is, right, if your volume V is 0, right, the height H should also start from 0, right? So your line should always start from 0, okay? And because of that, let's draw something like this as a line of best fit, okay? Something like that, okay? So just take note, right, this is a negative example. Don't do that. What I need to do is, right, take note, right, your ruler, right, should do this. And for a proper line of best fit, right, you should have a same number of plot points above the line and below the line. But in my case, I can't do that. So this is the best I can do, okay? So usually what I do is, in the model answer, you take a look over here, right? So 3 of the plots are underneath the line and 2 of the plots are above the line. This is about there. So about plus minus 1 on top or below, it should be okay. All right. So just drawing a nice thin line like this, you should be able to have your line of best fit, and you should be able to get your full 4 marks. This is a 4-mark question, right? So how do you exactly get all 4 marks for this, right? So 1 mark, the first mark is for when the x's are correctly labeled with the correct units. So yes, you see this line, this arrow over here for the x-axis and this arrow for the y-axis with the correct units and the units and the letters over here done properly, you should get your first mark. Even if you don't know how to draw a graph and you want to, you know, quickly get through it, done and over with, just take a ruler, just draw the 2 x's. Make sure you know the units are there. You should get your 1 mark easy, okay? Second mark is if you use a correct scale. So whatever I'm doing here, right, the 2, 4, 6, 8, 10, so on and so forth, and on top, which is the 10, 20, 30, 40, is if you make sure your graph is sensibly, you know, scaled, you should get your second mark, okay? Just don't use silly numbers like what, you know, 2.5, or should I say, not 2.5, sorry. For example, instead of putting 2 here, you put, I don't know, 7, 6 or 7 or so. No, it's not a very good, you know, scale for that. So it has to be sensible. It has to fit the graph, and the graph should you know, really be taking up at least 75% of the entire space they are given, okay? So this is just something I want to share with you. If your graph doesn't, you know, if your graph is not, you know, should I say, hitting 70% of the entire thing, you should not be able to get that mark, all right? So yeah, all right, that's fine. And let's move on, okay? So give me a second. Yeah. So if you draw the graph nicely, you should look like this. Okay. All right. We have the few jokers in the chat. Yeah. Okay. Yeah, I know. Yeah. All right. So okay. So let's continue. Right. Let's go to part D. All right. And in part D, okay, we are to determine the gradient g of our line, and we are to show all workings and indicate the values that we use. Okay, give me a second. My pen has problems again. Oh, well. Are you working? Yes, you're working. Fantastic. All right. So, all right. So for D over here, okay, determine the gradient g of your line. So we are to determine the gradient. So as you can see, right, gradients is just basically the change in the y-axis divided by change in the x-axis, right? So if you just, let's say, plot maybe a point at, say, 14 over here, and we take 0, 0, all right? So we have 2 points, 0, 0, and 14, and let's say this is 46 or something like that, okay? My graph is not the most accurate, but we can just use, let's use this, all right? So you can see, right, on 14 over here, it hits this line over here, okay? And right, so 40, 46, and this should be around here. This is not 46, this is 48. All right, so this is 48 over here at 14, right? So let's do this, right? So gradient should be equal to the change in the y-axis divided by change in the x-axis, right? And in the y-axis, we have seen over here, this is over here, this is not 46, this is 48, okay? So this is 48, which is the y-axis, the final, minus the initial, which is 0, divided by the x-axis, which is 14 minus 0, okay? Now let's push this into the calculator, right? And let's see what do we get, okay? So give me a second. I also still need to use my calculator. I'm not very good at mental sums. Divided by 14 should get, yeah, there we go. We should get this number, 3.4285, yada, 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 yada. Okay, we have a lot of numbers over here. But, of course, in Cambridge exams, right, you want to present your final answer in 2 or 3 significant figures, all right? In my case, I want to use 2 significant figures. So, let's see. First significant figure is 3, second is 4, third is 2. So let's write down, let's take a look at 2, which is the third significant figure, all right? So 2 over here is less than 5, right? So 2 is less than 5. So what we do is we round down, okay? We round down 3.4. So the number in two single figures is 3.4, okay? And then this is our gradient, and we have to make sure it has to be in two significant figures. And that's how we get the answer of 3.4, okay? Yeah? All right, so as long as you get 1 mark, as long as you use this sort of working, okay, like this, you should be able to get your 1 mark over here for your reading of gradient. All right, okay, so far everybody is good, yeah, looking good, okay, fantastic. So great. Let's take a look at the model answer. Yeah, as you see over here, this is not 46. My bad. This should be 48, okay? It should be 48, huh? And this should be 0, 0. So basically, this should be our answer, okay? Yeah. Right, so let's move on. Part E, right? The internal diameter D of a cylinder is given by the equation D is equal to K times square root of G, and where K is 1.13. So let's calculate D for the test tube. So let's take a look here. D is equals to K times square root of G, and K is 1.13. All right, so our G value is 3.4. So let's take a look at here. 1.13 multiplied by G, which is square root of 3.4. Now let's calculate this, okay? So square root of this multiplied by 1.13. And we should get this number, okay? We should get 2.09. That's a very, very long number. Okay, and now after this, as per usual, let's convert this into two significant figures. 9 is greater than 5, so we round this upwards this time round. So you get 2.1. 2.1, yep, 2.1 cm. Yep, right, there we go. Okay, and of course, let's write down two significant figures. Okay, fantastic. And now we can write 2.1 over here. Okay, so this is a 1 mark question. Same thing. If you get the answer is within 2.1 plus or minus 0.1, you should be able to get your 1 mark. Okay, yeah. So very, very straightforward. Yeah. Okay. So suggest one reason why your calculated value of D is only approximate. Okay. There's many answers to this actually. Let me just write down my answer. Okay. Yeah. The test tube is not, or should I say may not be a, right? May not be a perfect cylinder. Okay, yeah. So there are many answers to this. It's not just the perfect cylinder, all right? The gradient, for example, may not be, the gradient is actually very approximate. Could be just it could be a curve, right? Also, if you notice, right, the test tube, right, is curved at the bottom. So this equation doesn't really make sense, right? Also, H also will include the thickness of the glass. Maybe it's also difficult to get the ruler close to a test tube. Maybe the measuring cylinder only reads closest value to 1 centimeter cube, for instance, and also it's very difficult to judge the position of the water level in the test tube, so on and so forth. Any of these answers will get you your 1 mark. Okay, right? And once you're done with this, you are done with question 1, and you should be able to get hopefully your full 11 marks. Okay, right? So let's take a look if there's any questions from the chat. Okay. All right, we have a couple of jokers. Yes. Yeah. So to beat your allegations, this is not pre-recorded. I can do this for you. Okay. All right. So let's move on. All right. And also, am I going to do paper 4 as well? Unfortunately, this is our last ever section. last ever session with you guys. So if you want to see any more question, paper 4 solvings, right? Please go ahead to some of our previous live sessions where we have several paper 4 papers that are being live solved over there as well. So hope you see you there, okay? Yeah. And yeah, what is the value of x-axis here? Yeah, as Narayan sir has already replied you, please take a look over there, okay? Yeah, the scaling of the x-axis is 2, yeah, as you take a look over here, right? Each small square is 0. Each small square here is the scale of 0.2, okay? And the x-axis represents h, which is the height of the water, right? In the measure in the test tube, all right? And also this is measured in centimeters, okay? Yeah. So, oops, that should be this. Remember, it's just a test. It is basically measuring the height of the water, right, inside the test tube. Okay. Yeah. Let's move on. All right. I hope I answer your questions. And right, let's move on. Okay, to question number 2 for this. Okay. Give me a sec. Let me just get a bit of water. All right. So let's move on. Question number 2. All right. So a student, all right, over here investigates a light-dependent resistor or an LDR, and the student assembles a series circuit consisting of a power supply. Okay, we take a look at a power supply, a switch, a 470 ohm resistor, and an LDR. Okay, so figure 2.1 shows the part of the circuit that the student assembles. Okay, so we are to complete this whole circuit, right, by adding the correct symbol of an LDR between Y and Z, okay, in the list provided over here. So first things first, what exactly are these, okay? Right, an LDR pretty much is a light dependent resistor. So these are diodes. This is nothing, right? This is a LED. So this is also wrong. We don't take this. This looks a bit more correct. And this is wrong. So this is actually our LDR, okay? This is the correct one, huh? All right. So now that we have selected our symbol, let's slot this into Y and Z over here, okay? So as you can see over here, here's our power supply. This is our switch. This is the 470 ohm resistor. And our LDR should go somewhere around here, okay? Like this. Like this. And just draw the 2 arrows pointing into the LDR. Okay, this is not the cleanest job, of course. I'm not a good artist, but this should, let me just draw this nicely, yeah. All right, here we go. Okay, so there we go. This is the LDR. Okay, we put it over here, and as long as you select the correct symbol and put it into the circuit properly, you should be able to get your first mark. Okay, now let's move on to part B, okay? Part B, the student then now closes the switch, connects the voltmeter across the 470 ohm resistor, then they record the reading on the voltmeter, and then they open the switch, okay? So on figure 2.1, we are to draw the voltmeter, okay, connected to measure the potential difference across the 470 ohm resistor, okay? Right, so let's draw this over here. Where do we draw this? Okay, so we are to draw. Let's see. This voltmeter is connected across the 470 ohm resistor. Do remember, right? The voltmeter should always be connected in parallel to the thing you want to measure, the potential difference. So what you need to do is you can just draw one of these little blocks here, like this, V for voltmeter, and there you go. Okay, remember, please use a ruler. Don't do this. Actually, you know what? I should do it nicely, right? Let's do this nicely. Yikes. And all right, this and something like, all right, there we go. That's 1, that's 2, All right, nice and clean right here. And the voltmeter sits around like this. Okay, so pretty much that is how the voltmeter is connected to the 470 ohm resistor. Okay, this should be connected in parallel. Please remember that. Okay, right. By doing so, you get your 1 mark. Right, great. So let's move on to part 2 of our question. Right, the voltmeter reading is shown here in figure 2.3 over here, right? This voltmeter that we connected in parallel, right, is now showing this value, okay? So record the reading of the voltmeter. This probably is a piece of cake for all of you, right? Yeah. Each of these small little markings represent how many? This is, let's see, 0.5, this is 0.5 volts, so 0.6, 0.7, 0.8, so 0.8 volts, yeah? So this is definitely 0.8 volts, okay? Let's also make sure this is in 2 single figures, so we add a 0 behind, okay? Yeah, second significant figure. That should get you your 1 mark. Easy 1 mark lah. Oh, okay? All right, so let's move on to part C. Part C, right, the current in the circuit is calculated by this equation, I equals to V over R. I mean, you guys know this, right? V equals to IR. And then when you do some mumbo jumbo with the equation, you just move the values around a bit. You should get I, which is equals to V over R, right? There we go, okay? So where R is equals to 470 volts, ohms, I'm sorry, 470 ohms, okay? So we are to use our voltmeter reading in B part 2 to calculate the current I. All right, so let's do this. Okay, so we're given I is equals to Vxy over R, right? So let's put in the value of V. V is 0.80, okay? Divided by R, which is 470. And we should get a very tiny number, yeah, 0.01702, yada, yada, yada. And let's convert this into your usual two single figures, 0.0017, okay? And the unit is amperes, and of course is 2 significant figures right here, right? Because this is our third single figure, is 0, 0 is smaller than 5, so round downwards, so 0.17, okay? 0.0017 amperes over here, right? Let's write it down, 0.0017 amperes. You see, there's no, okay, do remember this, if there is no unit over here, you have to write down the unit right here, okay? Yeah, so 0.0017 amperes in 2 single figures. And how do you, this is a 2-mark question, so how do you get the full 2 marks? The first mark is if you write this, okay, 0.0017, all right, 2 single figures. Second mark is if you write your answer in amperes, right? This is your 2 mark done like this, okay? Fantastic. Now, let's move on to part D, okay? In part D, right, the student once again closes the switch and then connects the voltmeters between points Y and Z, okay? And then they record the voltmeter reading VYZ and opens the switch. And for, you see, VYZ is 2.2 volts, right? So we have to calculate the resistance RB of the LDR in bright light using this equation, okay? So same thing as per usual, RB is equals to VYZ divided by I, okay? As you do know, the current is constant because you see in our diagram is just one single pathway, right? The current doesn't split into 2 or whatever, so current is constant for the whole circuit, okay? Remember your series circuit, yeah? Right, so VYZ over here is, okay, 2.2 volts, right? Divided by I. I is this tiny little number right here, 0.0017, okay? And let's push this into the calculator. And we should get a big number, right? So we get 1274.117, yada, yada, yada. And of course, let's convert this into 2 significant figures as per usual. So let's take a look here. First, second, third. 7 is bigger than 5. We round this up. So 1300. What's the units for resistance? It's ohms, okay? And then let's write down to SF. right here, okay? Yeah, okay, so the answer is 1300 ohms, okay? There we go, right? Okay, so how to get your mark? Basically, if you write this down, you should get your mark, okay? Yeah, let's move on. Now, the student covers the LDR. Okay, what do you mean is, the LDR, right? Take the hand, cover. Now it's in darkness, okay? And with a piece of card, and then repeats the procedure described in B and D, okay? So, VXY is, what is VXY? VXY is this over here, okay? Right? The 470 ohm voltmeter, all right? So this is for the 470 ohms, okay? And this is for the LDR, all right? Now, we have to calculate the resistance RD of the LDR in the dark using this equation over here. So let's do that, okay? RD is equal to 470 ohms, okay? Multiplied by VYZ, okay? What's VYZ? 2.9 divided by VXY. XY is 0.15, okay? And then let's plug and do the maths. And let's see. Okay, we should get a very big number. 6666, yada yada yada. And of course, we have to do our good old rounding up or rounding down stuff over here. First single figure, 9, second is 0, third is 8. 8 is greater than 5, so we round up the 0. So we get 9100. Okay, what? This is the resistance, so it's ohms. Okay, so this should be our answer. Okay, 91. Oopsie, this looks not nice. So it's 9100 ohms. Okay, in two single figures. Okay, getting this number should get you your 1 mark. All right. Okay, now let's move on. Part 2. Okay, so next, the student removes the card from the top of the LDR and slowly lifts it vertically upwards away from the LDR until the card is like what, 30 cm, okay, away from the LDR, okay? The student observes and records the readings on the voltmeter across the LDR as the card is raised. So you take a look over here. The distance, basically this is the distance of the card from the LDR, and this is the potential difference, okay, across the LDR, okay? So as you can see, right, as the distance increases, the potential difference of the across the LDR decreases, okay? This is the first thing you need to take note of, huh? All right. So over here, we are to write we are to describe this very qualitatively, right? Describe, right, how the potential difference across the LDR, which is VYZ, changes as the distance between the card and the LDR increases. I just said that just now, right? So, firstly, right, as I said before, where is my text, right? Yeah, so the potential difference of the LDR decreases as the distance increases, okay? Right, that's the first one, okay? And the second one, okay, this happens until it levels out and remains constant at 2.2 volts at a distance of 20 centimeters, okay? Okay, so there we go. This is a 2-mark question. So writing these 2 points, right, will get you your full 2 marks, okay? So first mark is definitely this one, this point. Second mark is definitely this point, all right? So as I said before, if you look through this, right, the number actually stops getting smaller after 20 centimeters, okay? So this is the minimum potential difference across the LDR, all right? So yeah, so the basically as the distance increases, the potential difference across the LDR decreases until a certain point where it plateaus and it stops going any further lower. Okay, any lower, huh? All right, let's move on. Okay, so over here, part F, when the LDR is covered by the card, right, the current in the circuit changes. So we are to use the student's results from B part 2, D, E, and E part 1 to show how this change in the current affects the value of the total potential difference. Okay, so let's take a look at all our results. Okay, so when the LDR is not covered, let's take a look, right? At part B2 and D is when it's not covered, right? And this is when it is covered. All right, so let's take a look at when it's not covered. Okay, so when it's not covered, we have Vxy is 0.8, all right? And then Vyz is 2.2. So let's write that down. So when the LDR is not covered, right? Total PD, total potential difference is equal to 0.80 plus 2.2, right? And it should get you 3.0 volts, all right? And when the LDR is covered, right, total potential difference equals to, let's check this out, okay? Over here, the student covers the LDR with a piece of card, all right? So Vxy is 0.15 and Vyz is 2.9. So let's write that down, equals to 0.15, right, plus 2.9. And that should get you 3.05. And in two single figures, we get 3.1 volts. All right. So you see, right, when the LDR is covered and when the LDR is not covered, the potential difference across both components, right, added together is always around 3.0 volts. So it barely changes, right? So basically, let's write that down. So thus, even though, right, even though the current, okay, changes, right, the total potential difference remains almost constant. Right? So basically, if you write down, right, that the values of Vxy and Vyz, when they add together, the two values are constant or nearly identical. And if you have a conclusion, right, that both values are, that if you use the values from these from the questions correctly, you should be able to get your full 2 marks. Okay? Yep. And with that, we are also done with question number 2. So find any questions from the chat? Our answer, let me know if there's any questions from chat, yeah? Okay, looking good. All right, so far no questions. Fantastic, let's go on. Let's move on. All right, so let's move on to question number 3, okay? Yeah? Question number 3, a student investigates the image formed by a converging lens, and we are to refer to figure 3.1, all right? So the student switches on the lamp, okay, over here, okay. Thank you, Naransa. No questions, yeah? Okay, let's continue. Okay, figure 3.1 shows the lamp, okay. The student turns on the lamp, okay. Places a screen over here, right? This is a screen, okay. A distance D equals to 80 centimeters, okay, from the illuminated object, which is here, all right, which is a triangle hole in a piece of card, and he places, this is the lens, okay, close to the illuminated object, and then the student moves this lens away from the illuminated object, all right, until a magnified, inverted, and sharp image of the illuminated object, right, is formed on the screen. Okay? So, on figure 3.1, measure to the nearest 0.1 cm the object distance x, all right, from the center of the lens to the illuminated object. This one, once again, I need you guys to take note, right, that you are to print, please print, okay? Print this paper when you are working on it, because a lot of your skills such as measuring, drawing, everything to scale, right? This is where your skills about this are tested. So either you can, once again, print this from our website, ciepastpapers.com, or you can visit any of these past year paper sellers that sells and prints these things for you. Please work on this. Yeah, but of course I do prefer if you use it from our website lah. Oh, all right. So if you use a ruler and then you measure this properly, I've done so using a 1-to-1 scale thing on my computer screen. Yeah, and doing that, you should get x should be equals to 4.1 centimeters. Okay. Yeah. 4.1 centimeters is the length of x, okay? Yeah, so you just need to put x, right? You see already here, x already has been identified for you, so you just put your ruler, your 0 here, and you measure it whatever this whichever number that's over here, okay? If you don't get 4.1 in the 1-to-1 scale, I don't know, your ruler might not be very accurate, or you are not very accurate. All right, so let's move on. Part 2, okay? Part 2. 3.1, all right? Figure 3.1 is drawn to scale 1/5 of the full size. So this is scale 1/5, okay? So everything over here, right, that you have seen and measured, right, is a fifth smaller than the real thing, okay? Which means everything here represents something that is 5 times larger. So we have to calculate the actual object distance, big X. So we already seen here 4.1. 4.1 times 5 equals to 20.5 centimeters. Okay, so let's do that. 20.5 centimeters should be the answer. Okay, 1 mark for correct answer, 1 mark for correct answer. Straightforward, yeah? Okay, now let's move on. Part B. So the student continues to move the lens away from the illuminated object until a second sharp image, which is diminished and inverted, right, forms on the screen. And the student measures to the nearest 0.1 cm the object distance y from the center of the object of the lens to the illuminated object. So what do they mean? So they continue to move this lens all the way until let's say somewhere around here, okay? And then the image form is diminished and inverted. Okay, right? It's inverted and diminished, okay? So it's smaller, diminished means it's smaller, inverted means it's flipped over. Oh, okay. So if a triangle looks like this as the source, the image should look something like this, smaller, okay? So measure to the nearest 0.1 cm the object distance y from the center of the lens to the illuminated object, all right? So student measured it for you, you don't have to do it, thank goodness. Y is equal to 59.8 centimeters, okay? So this is what again? Object distance y, center of lens to illuminated object. Oh, so basically it's here. So up to here, this should be y, okay? Yeah, there we go. So figure 3.2 over here shows a illuminated object, okay? And so we are to draw a diminished and inverted image of this triangle on the space provided. As I said before, diminish means smaller, and inverted means if the triangle is like this, it should be like this. So use a ruler to draw this, don't freehand it, as I always say. So do it something like this, it should be a bit smaller, okay? Like this. Draw this with a ruler, okay? Right? So, all right. Now that is done already. Now let's calculate the value d equals to y minus x as in our over here for part B, okay? So let's take a look. Our value of x is 20.5, okay? So d is equals to y minus x, okay? X is equals to 20.5, y is equals to 59.8, so let's do that. 59.8. Okay, now let's do the calculations. Yada yada, and you should be able to get this. Okay, should be equals to 39.3 watt centimeters. Okay, all right. So this time round, right, we don't do two significant figures because the values that were given to you are in three significant figures, so we have to use that. Okay, yeah. So doing so, you get your 1 mark. And just now, if you draw a triangle that is smaller, right, inverted triangle, you should also get your 1 mark. Okay. All right, fantastic. Now let's go on to part C. Okay, part C. The focal length f of the lens can be found using this equation: f equals to d squared minus d, the big D minus small d divided by 4 big D. All right, so we have to use this value of big D from A and small d from B2 to calculate the value of f1. Right, let's do this. So f1 is equals to big D squared minus small d squared divided by 4d. So, do we have a value of big D? I think we do. Big D is 80 cm, right? As stated over here. Yeah, over here, big D is equals to 80 cm. Okay, so let's do that. Big D square, 80 square minus small d, which is 39.3 squared, divided by 4 times big D. Okay, now put this into our equation. Okay, let's take a look at that. And we should get 15.1734 yada yada yada. Now let's convert this into three significant figures, okay? Because everything is in three sig fig, we should continue that trend. Oh, right. So 1, 2, 3. So 1 and then 4. Fourth significant figure is 7. 7 is greater than 5. So we round up the third significant figure. So we get 15.2 watt centimeters. Okay, that's the value of f right here. So let's write down three significant figures. Okay, yeah, f is equals to 15.2. Done. All right, so this is a 2 mark question. How do you get your 2 marks? Okay, your first mark is if you write this down. Okay, the second mark is if you get 15.2. Okay, and also in three significant figures. Yeah. Okay, let's go. Continue. Part D. Ooh, okay. Part D. All right, part D. So the student repeats this procedure in A and B for an object to screen distance of D equals to 100. So basically, the light is here, the lens is somewhere down there, and the screen is now 100 centimeters away from the object. Okay, so the student records the value of x, y, and d to be these. Okay, now we have to calculate the second value of f, right? f2 using the equation of for the focal length of the lens using the equation in C. All right, let's do this. So the equation in C, what is it again? F is equals to big D minus small d, big D squared minus small d squared divided by 4 big D. All right, so f2 will be equals to d squared minus d squared divided by 4 big D. All right, so big D over here is now 100, so that's 100 squared, right? Minus d squared, which is 63.7 squared, divided by 4 times 100. Okay, now let's do the calculations. Push this in the calculator, and doing so, we should get this number. Okay, and we should get 14 point yada yada. And of course, let's push this into three significant figures. We should get, this is 8, right? 1, 2, 3. 8 was the third significant figure. 5 is the fourth one. Okay, 5 is greater than or equal. So 5 is equal to 5, right? So we round upwards. Okay, so we get 14.9. Okay, centimeter as our answer in three significant figures. Okay, the answer is 14.9. All right, you get this, you get your 1 mark. Okay, so the two quantities can be considered equal within the limits of experimental accuracy if their values are within 10% of each other, right? So state whether your values of F1 and F2 from C and D can be considered equal, okay? So what is your value of F1, right? So F1 is equals to, let's take a look, 15.2, okay? Right? F2 is equals to 14.9. So difference between F1 and F2 is equals to 15.2 minus 14.9, which is equals to 0.3 centimeters. And percentage difference, right? Okay, with F1 should be equals to, let's see, 0.3 divided by 15.2 and then multiplied by 100%. So are we within the 10% value? Yes, we are. Actually, it should be equals to 1.97%. Okay? Okay? Yeah. So if you take a look here, the percentage difference over here is actually very minimal. It's 1.97%. It's less than 2%, right? So state whether your values of F1 and F2 are equal. All right. So, okay. The two values F1 and F2 can be considered equal. Okay? Right? There we go. Because they are just within 0.197 of each other percent. Okay? Okay, so basically by calculating this, right, you get your first mark, and then you state that it's equal, you should get your second mark. And there you go. Okay? Yeah. All right. So with that done, we are done with question number 3. Oh, no. We are not done yet. My goodness. I thought we are done. All right. So let's go on to part F. All right. So state one technique to use when doing this type of experiment to ensure that the image on the screen is focused as clearly as possible. So what do you do, right, is if you notice, if you remember just now, right, they say they take the lens and move it towards the screen to achieve focus. How are you going to achieve focus? Of course, you don't just yoink it or just move it quickly to try and get focus, right? You have to move slowly to try and determine as sharp as possible, right? So pretty much, right, the student, right, should, right, move the lens, okay, forwards or backwards, slowly. Most important word is slowly, okay? It has to be slow, right, to bring the image to focus. All right? Just simply put, just do it slowly. Don't just rush it. Don't just yoink the lens towards the screen. You will never get focus, okay? By just stating this, moving it slowly, get your 1 mark, okay? Now, let's go to part 2, okay? Part 2, very straightforward. The experiment is usually done in a darkened room, right? A nice dark room, okay? Explain how this makes it easier to see when the image is in focus. All right. So why do we use a dark room for this kind of experiments? Is because, right, you want to make sure the image is as sharp and contrasty as possible. Am I right to say that? So it'll be easier to focus. It'll be easier to adjust your stuff, your lens properly. Unless you have butterfingers and you just knock everything over, that's a skill issue, I guess. So most importantly, a dark room, right? A dark room allows for better contrast, right? And thus, it makes the image, right, easier to focus. Ooh, there. That should not be there. To focus. There we go. Okay, just like that. All right, so basically this is just one way to answer this question, okay? So the other ways are basically, better contrast is one of it, right? Or should I say the other options are, the edge of the image are sharper, more visible, easier to see. Any of that will get you your 1 mark over here, okay? And just like that, hopefully you should be able to get your full 11 marks for this question. All right. So with that, I think we are done with question 3, yeah? Okay. Not the false alarm, huh? All right. Looking good. Okay. Now let's take a look at, let me take a look at chat. So chat, so far, all good, yeah? +2. Yeah, unfortunately, we don't do +2. We only do IGCSEs and the AAS and A levels for Cambridge. Yeah. So even though this is not your syllabus, thank you for joining us. Okay. Yeah. Let's move on. Now let's move on to question 4. Question 4 is usually the most worthy of the lot. Okay. Usually the most for some of you guys, the most difficult to do. Okay, so let's take a look at question 4. Okay, so over here, water is poured into a glass beaker and allowed to cool down for 5 minutes. Okay, so we put hot water into a beaker, all right, and cool for 5 minutes. Okay, right? Let's just write it down. If the thing is, right, how I do questions is I will draw and I will scribble all over my papers to, make things easier for me to understand. So if this works for you, please go ahead and do it, but don't write all this in, like, say, the answer parts, okay? And also, if you have spare paper, write over there, okay? Now, plan an experiment to investigate whether the rate of cooling of the hot water depends upon the initial temperature of water. So what that means is we need to plan for an experiment to investigate whether the initial temperature of hot water affects the rate of cooling of the water. Okay, initial temperature, rate of cooling. You see that? I underlined the 2 key things you need to take note. Huh? All right. So the rate of cooling of water can be calculated using this equation. Rate of cooling is equals to the decrease in temperature divided by the time taken. Okay? Yeah. So in this experiment, in this particular question, you are already provided with a supply of cold water, some electric kettle, a 250 centimeter cube glass beaker, and a measuring cylinder. And we are to include any other more common laboratory apparatus, right? So in our plan, right, in our plan down here, we need to include, right, what other apparatus is needed, okay? A brief description of how to perform the experiment, including what you need to measure and how you make sure your measurements are accurate, okay? What variables you control, which variable you will increase or decrease, okay? And the results to record all your measurements. And of course, you don't need to include any reading because you're not doing any experiment, yeah? And finally, how will you process your results to reach a conclusion? And you will be needed to include a label. You may include a label diagram, okay? Right, so let's take a look here. I usually don't draw a diagram for this, but we can do that later, okay? So, first things first, okay? What other apparatus we need for this? Wait, 1 second, let me just have a bit of water. Okay, let's do this. All right, so any other apparatus we need, okay? Since we are actually, investigating the rate of cooling of hot water, right? Basically, we need to find out what's the temperature of the water initially. So something is not there, right? Something is not there to measure how hot the water is. So we need, additionally, a thermometer, right? We need a thermometer, right? And of course, we also need a stopwatch, right? We need to find out how much it cools, right? So we need the time, how much, let's say you want to wait for things to cool for 5 minutes. How are you going to, how are you going to time yourself for 5 minutes, right? So you need a stopwatch, okay? So a stopwatch, a thermometer, okay? Yeah. Okay, good. So we need an additional thermometer and a stopwatch. So let's write that down, okay? Right here. Okay. So basically, we are investigating the rate of cooling of hot water, right? So, and this depends on the initial temperature of the hot water. So basically, a thermometer is required to measure the temperature of the hot water, okay? A thermometer is required to measure the temperature of the hot water, okay? And of course, we did mention, right, a stopwatch is required, right, to take the time taken for the water to decrease its temperature, okay? That's the first thing we need to take note, all right? So next thing, right? What are the variables you are to control? So first things first, right? What would affect the rate of cooling of water, right? So if you put your hot water into, let's say, a beaker, then the next experiment you do it in, say, evaporating dish, then the next one you put in a measuring cylinder, then that will kind of make the experiment doesn't really work, right? So you kind of want to ensure that the container used to cool the liquid down, right, to cool the water down, right, is constant. So the beaker must be constant, okay? The time taken for the water to cool should also be constant, okay? Right? That, and also next thing you need to take note is if you conduct one experiment in a nice cold air conditioned room and the next moment you do this experiment in a hot sunny day, this is going to be different as well, right? So the condition, or should I say the room temperature, should also be constant, okay? Room temperature should be constant, beaker should be constant. Of course, if you have, let's say the first experiment is 95 degrees Celsius, you use 50 centimeter cube of water. Then in the next experiment, let's say you put in 200 centimeter cube of water and it's a 90 degrees Celsius. This doesn't make sense, right? The rate of cooling will be different for different volumes of water. So the next thing we need to keep constant is of course, the volume of water. Right? So and also the room temperature, the beaker type. Okay, yeah. So basically, the beaker we use must be constant. The volume of water must be constant. The room temperature itself also must be constant. Okay, right. So let's write that down. Right. So over here, for this experiment to work, the variables that we must keep constant, right, are basically the volume of water used, right, as stated over here. Volume of water, okay, time taken, time given to allow the water to cool, the glass beaker where the water is cooled should also be consistent. So these three things we want to keep constant, okay? Yeah, right. So next, we have already found out what we need to, what are the variables we need to keep constant. Now, we want to briefly describe how we conduct this experiment, okay? So basically, we first put the cold water into the kettle to boil, right? If not, how are we gonna get hot water, okay? So first we boil the water to 100 degrees Celsius and then we measure, let's say, a certain amount of water, say 50 milliliters of water, 50 cm cube of water, and put it into a beaker, right? We use 50 ml of this water and put it into measuring cylinder to measure the amount of water, and then put it into a cylinder, into a beaker, and then we wait until the temperature hits 90 degrees Celsius, and then we start the stopwatch. Okay. So basically, this is how we do it. The first step, right? So once we have identified the additional things we need, right? We can now start the experiment. Right? So we can first do this experiment by Yeah. First, we add cold water to the kettle to boil. Okay. Of course, we have to boil a cold water to get hot water, right? And then we measure 50 ml using a using a measuring cylinder, and then use that and pour into the beaker. All right, and then of course when you pour everything in the beaker, right, the temperature will decrease over time. But the thing is, we want to let's say keep the variable you want to keep variable, right? The independent variable is the initial temperature of the water. So let's say we wait until the temperature hits 90 degrees Celsius, then we start the stopwatch for 5 minutes and wait for it to cool for 5 minutes, right? This is the first step, right? Right, so the next step is we want to, after 5 minutes, right, we can now take the final temperature of the water after it cools down, okay, and then record it into a table, right? And then this first part of the experiment is done. Now we are to repeat the exact same steps again, but with temperature that is lower. For example, 80 degrees, 70 degrees, 60 degrees, 60 degrees, so on and so forth. Okay, you can also add cold water into the hot water to have a much to control the temperature better for, let's say, 50 degrees Celsius. Yeah. Okay. Now that is done already, we can finally record data. Right. Then, of course, with the data collected in the table that is I'm going to show you later. Right. We are going to draw a graph of cooling versus the initial temperature to obtain the line of best fit. There we go. Okay. Now let me show you how to do the graph. Okay. The graph is not graph. Sorry, we're going to show you how to do the table. So let's say we have the initial temperature. Okay, and that is in degrees Celsius, right? We also have a final temperature, also in degrees Celsius. All right, and then we have a decrease in temperature. Okay, wait, let me just write this nicely. The decrease in temperature is basically the initial minus the final temperature. And finally, we need to have the rate of cooling, which is let's take a look at the rate of cooling, right? The rate of cooling over here is stated as decrease in temperature divided by time taken. So decrease in temperature, which is degrees Celsius, time taken is in minutes. So it's degrees Celsius per minute. Okay, this will be our headers for our table over here. Okay, the table is not going to be very, very nice, so let's just draw it like this. Okay, something like this: initial, final, decrease, rate, and then like this. Okay, and then of course initial temperature you can have 90, 80, 70, 60, and 50, and so on. Okay, you should have at least 5 data points. Okay. Okay, let me just redo this thing a little bit. So we should draw a graph of rate of cooling versus the initial temperature to obtain the line of best fit. And there we go. Okay, just like that. Okay, right, so drawing something like this, how are we going to get the full 7 marks for this question? All right, so let's take a look at the marking scheme. Okay, so 1 mark is awarded for a stopwatch, a timer, or a clock, of course, to keep track of time, and also a thermometer, a temperature probe, or a sensor. Any one of these, okay, will get you your first mark. Basically, the additional equipment you need. The second mark you need, right, is the correct method. How are you going to conduct the experiment? So step 1, heat water to a certain temperature, right? Time the water cooling for 5 minutes and then measure the final temperature of water. Yeah, and then 1 mark for repeating, right, the experiment with a new value of initial temperature. So for example, if your first initial temperature is 90, the next experiment you do should be, let's say, 80. Should be then the next one is 70, 60, 50 downwards. And then you repeat this, basically repeat each experiment as with a decreasing initial temperature. All right. And then next, your next mark is given for one control variable kept constant. We gave two actually, so that's fine. So the two variables we kept constant are the volume, the mass, the amount of water that we use to cool, the time taken to cool the water, and also the room temperature of the surroundings. Yeah, these are some of the things we need to keep constant. Okay. And next, we are given 1 mark if we have a table with clear columns with initial, final temperature, and also with the decrease in temperature, and also the rate of cooling, and also all the proper units inside. So as you can see over here, degrees Celsius, degrees Celsius, degrees Celsius, degrees Celsius per minute. Once you do all this properly, we should get your next 1 mark. Okay, and next, 1 mark awarded for a proper conclusion. So we are to plot a rate of cooling versus the initial temperature, or you can compare all the results in table to check how initial temperature affects rate of cooling. So I will write down to draw a graph, plot the graph to observe the graph of best fit. Yeah. And last but not least, right, the final mark, right, is you can either, right, set a second control variable, have at least 5 sets of data, repeat each experiment and take an average, which I didn't do, and evidence of the rate formula used. So either one of these, you get your final mark, right? So doing all of this basically will get you your full 7 marks. And we are done. All right, so hopefully this helps you to solve these 4 simple questions for paper 6 too, okay? So let me take a look at the chat to see if there's any other further questions. And from the looks of it, no further questions. That's great. Okay, that's it. So that's all, folks. Thank you guys for watching. And let me just yoink this back on and put this back here. So once again, I'd like to thank everybody for joining us in this session. And I know it's been quite a while. Usually we take about 1.5 hours to solve paper 6 question. So hopefully you guys can follow and keep track, okay? So, right, so for the students who will solve this paper together, I hope this really helps you. And once again, I'd like to nag, right? Please print this paper in order to, practice this, all right? A lot of the skills that I have mentioned, such as measuring and drawing, it requires you to actually, print the paper out and draw it to scale. So please do that, okay? And now before I wrap everything up, special mention to Homeschool.Asia, basically our so-called sponsors for today, right? Homeschool.Asia is basically the best experience for studying the Cambridge syllabus for the IGCSEs and the A-levels. And we have several subjects, mainly physics, mathematics, biology, chemistry, right, for the IGCSEs and the A-levels. And as for the A-levels, we also have econs and accounting, economics and accounting, yeah? So each subject will give you over 100 videos, right? And they will teach you all individual topics in excruciating detail, right? Including how to solve difficult questions found in examinations such as this, as well as a mountain of resources, such as, self-generated test papers, revision notes, diagnostic quizzes, and everything that will make sure you get an A for the subject, right? As for this paper, right, I obtained it from ciepastpapers.com. And every single latest test paper, right, past year paper from Cambridge can be found there for free. So if you want to practice more papers like this, or you want to, work on something like, paper 4.2, please go there and download the papers. In fact, right, the answer key for this paper, all the model answers, will be available there later. All right, in 1 to 2 days, it will be there. All right, so please go ahead, click the links down below, and please go to Homeschool.Asia to explore your learning and get that A's for that subject you really, really wanted. All right, and last but not least, to my staff, thank you, Narayan sir, for always being a very stalwart supporter in the chat section, and of course the team for another very successful stream. Now, as you know, this is probably the last stream for a very, very long time. So I hope all of you guys, you know, take this as a good opportunity to practice and to also, study hard for your exams, and wishing you all the best for your upcoming examinations. Good luck, and wishing you all good night, good evening, good afternoon, good morning to wherever you are. And see you next time. Okay? Bye bye. See you soon. My throat. Where is my